for modern driver assistance programs. The floor is yours.
So thank you for the introduction. First of all, I'm not already a doctor, I'm a PhD student. So for everyone. So yeah, welcome to you to my presentation.
It'll change soon.
Okay. I hope, I want to welcome you to my presentation about probabilistic modeling of sensor properties for generic fusion systems. I want to start my talk with the questions: why do we need such a generic fusion system? State-of-the-art fusion system looks similar like this. There are several sensors which deliver their measurements into a processing chain, and there are many steps: pre-processing, detection, data association, and fusion and tracking. And yeah, unfortunately, all of these steps need knowledge about the sensor, which is programmed explicitly. We need some decisions, we need thresholds. I don't want to say that this method is worse than some other methods, but the problem is if we want to make a generic fusion system, if we want to exchange some sensors, it's very hard to do if the whole fusion system depends on this knowledge. So the only way to do this is to transform this knowledge somehow into the sensors. So our proposal for this for fusion system, which can be generalized, is it looks like this. We have several sensors. For example, ESP data for ego motion estimation, and a camera and a laser scanner. Maybe there could be more sensors, and all these sensors deliver their measurements again in this probabilistic generic fusion kernel, which is based mainly on a GI-PTA algorithm. And afterwards, several applications can get their environment model, which is modeled probabilistically at the same time. So doing this, we have to provide a probabilistic interface between sensor and fusion system, and between fusion system and the applications. So now we are able to exchange some sensors, for example, a laser scanner and a radar, by a radar. So these probabilistic interfaces have to provide several information. On the application side, this interface has to contain the whole object information over time, which means the position estimate, the spatial uncertainties, and a kind of track quality measure. We are using probability of existence for the track quality measure, which is depicted in this image. The color coding is from gray to green. The more it's green, it's more probable to be existent. And the real environment model could look like this image on the right side. So on the sensor side, we have a different view. First, we have to think about what has to be contained in such a sensor model. The first thing is the measurement principle has to be modeled somehow, and the spatial measurement uncertainties of the sensor have to be considered. But this is, I think, state-of-the-art. This is nothing new. The harder things are the uncertainties which are on the existence side. So, for example, how sure has the sensor detected a model, an object? So on the left side, the sensor is very sure that he has detected a real object. On the right side, it has to deliver the knowledge that it is not really sure about the detection. So the second one is how likely is the sensor able to detect an object? So in some situations, the sensor cannot detect an object, but it's not a problem if it says it cannot detect the object. So the fusion system can react to this situation. And we have to create somehow new objects. And this has also be provided by the sensor. So the way when and how new the object be created. So this sensor-specific properties have to be modeled in any way. So one possibility is we use this kind of 4 cases. We have true positive, we have the false alarm case, we have misdetection, and we have true negative cases in any detection system. So 2 of them are error detections, type 1 and type 2 errors. And if we now have statistics about this sensor properties, we can calculate 2 important parameters which describe the whole sensor properties. These are the posterior probability for the false alarm case, and which can easily be derived from this table, and probability of detection, which can also be derived from this table. And these 2 parameters are enough to describe the sensor detection properties. Afterwards, we have to provide a method on how to fuse this existence information from several sensors into a sensory-based existence estimation of track existence. So for this, we use a graph-based GIPDA algorithm. Unfortunately, I cannot go into details. So we have several papers published about this thing. Please have a look at our paper references. The basic idea is we are creating several hypotheses between an object and a measurement assignment. So for example, the first one denotes the case that object 1 is assigned to measurement 1 and measurement 2 is from an unseen new birth object. And the second one is, again, object 1 is assigned to measurement 1 and measurement 2 is caused by a Glattis source and so on. And so we are enumerating all possible cases of events, and this can be done in a large tree. And afterwards we can calculate probabilities for all events by multiplying the probabilities of these nodes from a root node to a leaf node. And again, for the probabilities of these nodes, I would to invite you to have a look at the paper, so I cannot go into details. Afterwards, we can derive the probability of existence after having integrated all sensor measurements for a time step. So how can we model these sensor-specific properties? For an example, I want to show you the probabilistic sensor model for a mono camera. We also have probabilistic models for a laser scanner and for radar. This example is based on a cascade classifier based on Viola-Jones for vehicle rear and front views. We have a measurement vector consisting of I, J, and W. This is the pixel position and the width of the detection. And as existence measurement, we use the size of the detection cluster. So if the size of the number of detections, E on the left hand, is high, there's high evidence that there is a real object, and if it's not, like on this right side, there's a low evidence. This can be transformed by large statistics into a relative frequency, and so we can derive the posterior probability for the false alarm case for this kind of sensor. The second parameter is the probability of detection of this camera, and this probability of detection depends on several things. For example, the object position in the field of view, horizontal and vertically. For example, on the left image, this car cannot be detected by our sensor, so the probability of detection has to be very low. And on the right side, unfortunately, our detector can also not detect the object because we cannot see the whole object. But this depends, of course, on the detection on the video detector. So also because it's a rear and front field detector, it is hard to detect oriented objects. So this can be also modeled in this state-dependent probability of detection. Distance of the object is also a very important part, but I will neglect it here. So the object orientation to the camera is can be modeled like this. We have a state-dependent probability of detection, which is depends on the orientation to the line of sight, and we are able to derive the detection probabilities based on large statistic databases. And the result looks similar like this. Afterwards we can model the detection probability like it's written here. So we have two thresholds. If the orientation is lower than a certain threshold, we have a priori probability of detection, and if it's higher than the second threshold, we have no detection possible, and between it's modeled as a sigmoid function. The position of the object in the field of view is can be written like this. It's written as part of this probabilities. Unfortunately, the position of the object is contains uncertainties. We do not know the correct position, so we have to derive this probability as a function of other probabilities. This can be done really efficient. There's only one integral left after doing some simplifications, and this can be simply approximated with numeric methods. So what we gain after this is can be visualized like this. The probability of detection is color-coded from black, which corresponds to 0, to white, which is 1. The field of view of the camera is the red line, and as we can see, there's a shadow region in the field of view of the camera, which is very large. This is a field of view of about 20 degrees. It's a telefocus lens, and so we have a very narrow field of view. The second or the third interesting part is the object birth model. We have to somehow create new hypotheses for new objects, and these are created by measurement data. For example, we already have two object hypotheses, and then we get, for example, from a laser scanner, we get two L-shaped measurements. And the question is now, are we receiving the measurements from two new objects, or are they the same objects as we already have? If we regard the spatial uncertainties of these objects, this question is not easy to answer. In addition to this, if we regard the existential uncertainties, the problem is even worse. So we have to contain both spatial and existence uncertainties in one model. So one thing which is known in literature is the probabilistic hypothesis density function. That's a spatial description about the spatial uncertainties and the existence uncertainties. So the integral over some region in space integrates to the expected number of objects, which is in our case the existence probability. Unfortunately, this is only defined for point targets, but we have extended targets which have length, width, and height, and an orientation, of course. So we have to convolute this Gaussian probability hypothesis density function with an orientated object box model, and afterwards we get a description like this. This is again a dimensional PhD function with a high existence probability, and this is the same spatial uncertainties but with a lower existence probability. And this function accounts for both spatial and existence-based uncertainties. So now we can derive probabilities of birth for example, this situation. What we want to have is a probability of birth which looks like this. Black regions are very unlikely to produce new targets because there are already targets, and in the white region we can create new targets. The probability of birth is based on three parts. The first one is based on a current environment model. Additionally, we can add information out of high-level information, for example, if we have digital maps available or lane information or something else. And the resulting probability of birth can be written like this. The first part is the posterior probability for the true positive case, and these parts are those from the slide. And what we get is one of those node probabilities from the hypothesis tree that I have shown you at the beginning. So I come to some results. We have an exemplary sensor setup based on ESP data. This camera with this Viola-Jones cascade classifier and the laser scanner which extracts line features from the raw data. Afterwards, we use this GIPDA-based fusion system. First of all, we have evaluated the real-world data, some dependencies on this model of the probability of detection. The dotted line denotes the mean time confirmed over the false alarm rate. The false alarm rate is we have a dependence on a threshold of probability of existence, so we can vary the false alarm rate of the system, and the mean time confirmed is the time which is a track over a certain probability of existence. So what we can see is that constant modeling of a probability of detections results in a very low mean confirmed time. Instead of this, we could model the state-dependent probability of detection, and we get a much more mean time which this track are confirmed. So afterwards, because I think this videos show more intuitive results, I have a first video. What we can see here is whoops, this was too fast. The magenta boxes are detections of the Viola-Jones cascade classifiers. The blue lines are the segments out of the laser scan data. The top right view shows the bird eye view of the laser scan raw data, and the bottom line is the resulting environment model. Again, our tracks are color-coded from gray to green, and in this view we have the back-projected tracking results in 3D. So this is the first approach using a constant probability of detection only inside the field of view. Again, what we can see here, the blue lines are the field of view of the camera, and yeah, it's quite obvious that we can't detect the taxi which is driving in the right in front of us because it's outside of the field of view. If we model the detection probability correctly, we can, of course, track objects which are outside of the field of view of the camera. We can track oncoming cars when they leave the field of view of the camera, and which is something which is very interesting. The car can be tracked very nicely, but the Z direction is very uncertain. And if we get an innovation of the video sensor, we can correct the position very easily. And all this can be done without adjusting anything in the fusion system. It's only done by modeling the sensor properties. So I come to my conclusion. We have shown a way of how sensor properties can be modeled probabilistically. We are using probability for false alarms. We are able to model the probability of detection, and this is enough to create a way on how sensors provide a probabilistic interface. We have shown an explicit model for object birth, which can be processed also probabilistically. And of course, this system is able to perform in real time. And so we are able to exchange sensors by another without adjusting anything in the fusion system. So thank you for your attention. I'm looking forward to questions.